From the outside, it looks like an arms race. Every few months, a new model, a new name, a new benchmark shattered. But behind the scenes, something far less revolutionary is happening. The transformer architecture was introduced in 2017, and despite everything you have seen since, every breakthrough headline, every product launch, every viral demo, everyone is still using that same foundation. The core design hasn't changed. Over the past 5 years, AI companies haven't replaced the transformer, they have patched it. You see, each company added its own tweaks, small optimizations, clever tricks, mathematical band-aids. Each patch brought a little more performance, a little more scale, a little more runway. So let me quickly walk you through the most important ones. The first major breakthrough was brutally simple. More data gets you better performance, and better quality data also gets you better performance. After all, garbage in, garbage out, right? This realization triggered the era of massive dataset collection, filtering, and curation. Then came scaling laws. Researchers discovered that bigger models with more parameters generally perform better, but only if data grows with them. This led to compute optimal ratios, most famously the chinchilla rule, 20 training tokens per parameter. Models got deeper, aka more layers, models got wider, aka more attention heads. Simply, performance improved by making the engine bigger. Next came alignment. Models didn't just need to predict text, they needed to generate response and behave in certain ways for different tasks. So companies introduced SFT, supervised fine-tuning, RLVR, reinforcement learning with verifiable rewards, RLHF, reinforcement learning with human feedback, DPO, direct preference optimization, among many. To put it in simple terms, AI companies began hiring domain experts, translators, doctors, lawyers, educators, to curate data and guide model behavior within their specific domains. In other words, humans teaching the model how humans prefer answers to sound in different situations. This made models safer, more polite, and more useful. Then mixture of experts arrived. Simply, different parts of the network specialize on different domains of knowledge. Each subnetwork acts as an expert and specializes. And when generating a response, instead of activating the entire network every time, only the relevant specialized subnetworks turn on. The result? Lower compute per token, better specialization, but the core engine remained the same. Some improvements focused on inference, for example context caching, which includes KV cache reuse introduced in late 2024 by DeepSeek. To put it simply, the idea is that we don't have to recompute the full attention pattern for every response generation step. Instead, we can store intermediate values in cache memory. This cut latency and reduced inference cost. Then come chain of thought, originally proposed by Google Brain in 2022, but made famous in 2025 with DeepSeek's R1 model. The idea was simple: force the model to think out loud by fine-tuning it with datasets that are structured as step-by-step answers, and by rewarding the model when producing intermediate chain of reason. The result? A model that starts reasoning step-by-step in plain English. As models grew deeper, they became unstable, so in 2026 DeepSeek introduced manifold constrained hyperconnections. To give you an intuitive understanding, a model is composed of many deep layers. Those layers are connected by bridges called residual connections. Traditional residual connections were unconstrained and chaotic, creating numerous unstable paths for learning signal to flow. DeepSeek's manifold constrained hyperconnections imposed a form of structure on these paths, which guide learning signals more efficiently, enabling stable training at unprecedented model depth. A brilliant fix, but still a fix. Another patch emerged in 2026, recursive prompting and recursive language models. Instead of feeding a long prompt directly into the model's fixed context window, an RLM places the entire context as a variable within an execution environment. The model then interacts with this data by writing and running code. This enables effective context window sizes of millions of tokens. Traditional transformer models process reasoning and knowledge retrieval through the same network, whether it's thinking or remembering. DeepSeek proposed something different. Instead of forcing the model to store everything inside its weights, it introduced a conditional memory. Attention computes a context-dependent embedding, the model's current thought. That thought is then used to query a memory system, retrieving only a small relevant subset of stored representations. In principle, it's simple. For a given thought, the model performs a fast lookup in a separate database rather than activating the entire network. Despite their impact, all of these advances are fundamentally patches. They don't address the core flaw of the architecture which power all these generative AI models. Most performance gains still arise from scaling data, scaling parameters, and scaling compute. Additionally, they help models scale further before hitting plateaus, but they do not change why those plateaus exist in the first place. So despite all these patches, the core architecture design remains unchanged, and so do the problems. Compute inefficiency, massive data redundancy, escalating energy demand, and black box reasoning. These aren't bugs, they are consequences of the architecture itself.